So we've got these three laws. Now, the first of these is really easy to understand for anybody. Law of conservation of mass. It means that we can't create mass, we can't destroy mass. There is no new mass anyplace. All the mass you've got today is all the mass that's ever been. Now we can change forms, we can move it around, we can rearrange it, we can shuffle it, we can turn it back and forth into energy. That's a whole separate thing. But in an ordinary chemical reaction, in an ordinary physical change, we don't create matter, we don't lose matter. When I said that you guys had created matter in one of your labs, it's kind of a joke. You can't create new mass. Okay. The law of definite proportion. This one's also easy to understand. So if we take a sample of water from a river in London, if we take a sample of water from a glacier in the Alps, because remember this is mostly happening in Europe, that chemical compound water, no matter where it comes from, is going to be roughly 11% hydrogen and roughly 88%, 11 point something and 88 point something percent oxygen. By this time, by the 1790s, they had isolated oxygen and hydrogen. They knew that those two things existed. Remember, prior to that, we didn't even know that there were different chemicals. It's all just stuff. So at this point, they know there's oxygen, they know there's hydrogen. You can look at water, and no matter where you take it from, it's going to be composed of the same percentages. And they find other chemicals for which this is true. And no matter where you take it from, it's going to have the same composition. So this is the law of definite proportions. Always those same proportions of substances. Those first two are really easy to understand. Agreed? Conservation of mass, got it. Definite proportions, got it. Here's the one that's a little bit trickier. The law of multiple proportions. If two or more different compounds are composed of the same two elements, then the ratio of masses of the second element combined with a certain mass of the first element is always a ratio of small whole numbers. Ugh. It's dense. It's horrible. It's hard to understand. So let's step back and break that down a little bit. If you think about carbon monoxide and carbon dioxide. At this point, they know that carbon is a separate chemical from oxygen. So you can take a sample of this gas, carbon monoxide, you can break it apart. You can take a sample of this gas, carbon dioxide, you can break it apart. You can isolate the carbon and the oxygen. If we do that, for a certain mass of CO, we find that this breaks apart into roughly 12 grams of carbon, roughly 16 grams of oxygen. Okay, well let's take the other gas, break it apart. Roughly 12 grams of carbon, roughly 32 grams of oxygen. So now let's look at the ratio of oxygen in those two compounds. 2 to 1. You got twice as much oxygen in one as you do in the other. Okay, but if you start to look at a lot of different compounds, you start to find that it's always 2 to 1, 2 to 3, 3 to 5. It's these little whole number ratios, which starts to indicate that there's some subunit. There's some piece, there's some chunk of oxygen. So rather than there just being a balloon full of oxygen, that balloon full of oxygen must have individual pieces that we can break apart. And this is observed again and again and again. So then, John Dalton, who's an English school teacher, 1808, and he's doing some pretty good chemistry work on his own. He takes a look at those three laws and he says, you know what, I think I have, this was a hypothesis at this time, to explain why those three laws are true. So remember, laws don't prove anything, they just state facts. Dalton has a working hypothesis. Dalton thinks he can explain why those laws are true. So first of all, he says that all matter is made of these little tiny pieces called atoms. So he goes back to Democritus's word, atomos, and that gives us atoms. So he says all matter is made of these smaller pieces called atoms, and any atom from the same element, so an atom of gold and another atom of gold, are going to be identical. Identical in size, identical in mass. They are completely identical, and they're different from an atom of steel, or an atom of iron, and an atom of copper. Okay? He also says, in the course of a normal chemical reaction, you can't just create atoms, you can't destroy them, and you can't divide them. And atoms and atoms and atoms. It's a chunk. So, imagine for a gold atom, you have a little G running around. Can't break it up. That's it. It's an atom of gold. He also says that we can take those different atoms and we can put them together. There are those simple, small ratios. 2 atoms of this, 1 atom of that. 3 atoms of this, 2 atoms of that. We can combine them, and that's what's really forming compounds. He says that when we run a chemical reaction, what we're really doing is we're just pulling apart the little atoms that are clustered together, and we're switching dance partners. We're switching them up. We're rearranging them. These new compounds are just new combinations of atoms. That's all they are. So, I'll tell you what, Dalton did pretty well. This is pretty good. I mean, he's going on strictly observational evidence. He's making a lot of inferences. He does a pretty good job. Now, with that said, a lot of what he had to say is still the basis of atomic theory. There are a couple things that he didn't have right that he couldn't possibly have known. So the modern additions to that. We, of course, know that you can divide an atom, but then you don't have an atom of that thing anymore. So the big atoms that we most commonly divide, things like uranium, plutonium, the big radioactive atoms, you can split it, but then you've got 2 atoms of new things. The other thing that he didn't know and couldn't have known, the tools weren't good enough for him to determine this, is that we can have 2 hydrogen atoms that have different masses, and we call those isotopes. We'll talk more about isotopes in the next chapter. He couldn't have known that. Honestly, with the tools he had and the time he was working, he did a pretty phenomenal job. It's pretty impressive stuff. Of course, he was building on the work of other people. All those people who were doing quantitative chemistry, he's building on their work. So it's a collaborative effort, but he gets the credit for that piece. Okay, so at this point, as far as Dalton knows, as far as we know, as far as the state of chemistry, the atom is a single chunk, might as well have its name stamped on it, so we have a brick that says iron, and that's an atom of iron, and we have another brick that says gold, and that's an atom of gold. And there's nothing below that level, except that people are starting to see things that make them suspect that there are. So, this is a cathode ray tube, and we're going to watch a quick video on the cathode ray tube. How many of you saw the term cathode ray tube? Actually, let me pause this. Have all of you ever seen a cathode ray tube before? A few of you think you have. Where'd you see it? Can you point to? Television. Yes. So, a television like the one we have up there, the big boxy televisions or big old computer monitors, those are a cathode ray tube. It's a glass tube. All the air's been sucked out of it. When you suck the air out of something, what do you leave behind? A vacuum. Starts with a V. Yeah, you leave behind a vacuum. That's a cathode ray tube at its simplest. And the demo you're going to see here is a different kind of...
We need a high voltage power source, such as this one.
Oops.
We need the Crookes tube, which has a metal cathode, a metal anode, a screen that has been coated with a phosphorescent material that gives off light when struck by electrons, and a bar magnet. As we turn on the screen, we notice that the electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated. We can use a magnet to show the deflection of that stream.
Here we can see the electrons being deflected by the magnet. The cathode ray moves upward. If we reverse the magnet, we would predict that the beam would be deflected in the opposite direction. And we observe that the beam is deflected downward.
Okay. So, we have these things called cathode ray tubes. Great.